One of the first things that we did when we started talking about exponential functions was we talked about calculating interest. And we'll use a new example here compared to the one that we used before, just with some bigger numbers because we're going to be looking at some differences that otherwise would look pretty small. So we're going to say that we're investing $1 million at 2% interest, and we're going to leave it in for 1 year. And this is the formula that we've been using to calculate interest. So A, the amount that you end up with equals P, the principal, which in this case is $1 million, times 1 plus R, in this case, the rate is 2% or 0.02, over N. So depending on whether we're doing yearly, if we're doing it yearly, then it's just once per year. If we're doing monthly, then N would be 12. So we're getting a 12th of the interest, but 12 times as often. And if we're doing it daily, of course, then N would be 365. And here's what we would come out with calculating each of these three ways: yearly, monthly, and daily. And we can tell that we're kind of hitting a little bit of a wall here. You know, we've gone from 1.02 million, and then by doing it monthly, we add another $184. But even by doing it daily, we only added another $16. That's not a whole lot. And so this brings up a question. What if we compounded interest, not just even every day or every hour or every minute, but literally continuously at every possible instant? The tiny, tiny little bit of interest that we earned in that fraction of a second got immediately thrown back into the account. And then we calculated the interest again, the tiniest fraction of a second later. Well, what would happen? Would this just get very slightly higher, or would we sort of unlock a whole new world of infinite growth if we are literally compounding interest every instant all the time? Well, to understand this and to calculate, in fact, what would happen, we'll go conceptual for a minute here. Forgetting the exact numbers, this is basically what we're trying to figure out. And this is probably new notation to you, and you don't need to worry about it, really. What we're trying to figure out is what would happen to this general expression. Like, don't worry about what the numbers are. We're just going to put a 1 in there. But when we divide something into n pieces, but then raise it to the n power, this is what we're doing with all of our compound interest calculations, taking the rate and dividing it, let's say it's monthly, into 12 pieces, but then that to the 12th power. So what happens if we sort of figure out, well, what if n were basically infinity? And that's what this means. Is there a limit to like what the value of this expression will be as n gets higher and higher and closer to infinity? So let's just put in some numbers and see. So over here, I've put in basically n equals 10, 100, and 1,000. And we can see it kind of seems to be certainly not like getting giant and, accelerating towards infinity or anything like that. It sort of hits a little bit of a wall around here. It's just not getting that much higher. As we go from n equals 10 to n equals 100, it's sort of stalling out in this weird place around 2.718. And sure enough, if you did actually put in infinity, or the largest possible number in here, the value of this expression would be about 2.718 and a little bit of decimal stuff after that. It's an irrational number. But it turns out this is a super important number in math. It's a number that we give a letter to. We refer to it as E. So just like pi is a Greek letter that represents a certain number, E is a regular letter that represents a certain number. In this case, 2.718, et cetera, et cetera. Really important number in math in a lot of ways. There's a button for E on your calculator or on the calculator on your phone. If you type E in Desmos, it uses that value, because what this represents is basically anything that is growing continuously. We've talked about things like interest that are actually calculated on a monthly basis or a yearly basis, but the vast majority of things in the world and in nature aren't like that. Populations don't sort of change at the end of each month. they just keep growing. They grow continuously. And so this number, this value E that describes continuous growth, is really a very fundamental number in all kinds of practical applications for like basically anything in the world that grows. Okay, so how do we use this number? Well, this is the formula for continuous compounding or continuous growth. And so let's figure out, going back to our original, question here, what happens if we have $1 million at 2% annual interest for 1 year, and we compound it infinitely often, every possible instant, it is always being compounded. That's what this formula tells us. So A equals P, there's our principal, $1 million, times E, and E is raised to the power of the rate, 2%, times the time, and in this case, it's just 1 year. And our result here, we come out with 1,202,000. I'm sorry, I wrote that wrong. There's a zero there. 1,020,000. There we go. 201.34. And let's just compare this to what we had before. So I'll write it on the first page as well. So it was 1,020,201.34. So you can see, compared to this interest being calculated daily, if we go through not just hourly, not just minutely, not just secondly, but literally at every possible instant, interest is being compounded. Well, on $1 million, it makes, what is that, 56 cents of difference over the course of a year? Not very much, although it's not zero, it is different, right? So this is compounded continuously is what we would say. And I'll write that here. This is when it's being compounded continuously. And so you'd think, before you knew the math on this, you would think, well, if you compounded something infinitely often, maybe that's like some trick where you'd end up with an infinite amount of money or something like that. It turns out it's not the case, because this expression, this source of this number E, it levels off. It maxes out at this weird, seemingly random value of like 2.718. And that means that no matter how frequently we compound interest on some amount, it's going to level off and have a ceiling to it as well. Now, we're not going to use E a whole lot. We will have some questions with it. We'll have questions like this. But in scientific applications, almost any exponential growth or decay is in fact modeled using E, because it is the actual way that something that is growing or shrinking continuously actually behaves.